Let's see, we have 6 people here. That's probably enough to start. So this lecture was, I don't know what to say about it. It has had 85 slides in it, and the poor postdoc was just racing through those slides, you know, and I don't think it was a very effective lecture, but it did sort of throw out a lot of topics and so on. And I must say that I did no more than listen to the video carefully. I did not follow up on all the papers. And let's see, now I gotta mute somebody. No, I fixed, I thought I set the meeting, I reset the meeting parameter so that everybody gets automatically muted on entry, but I don't know if that worked. Anyway, yeah, so I went through this thing, the video carefully. I didn't follow up on any of the papers, and it turns out that, you know, she was in such a hurry that she had to skip a whole bunch of slides in during the, you know, she had to skip over a whole bunch of slides in order to finish in 2 hours. And I must admit that I didn't go over the slides that she skipped. So all I can do is just go over what I, you know, go over what I did see and try to make sense out of it. Okay, so the first thing she just gives a recap, which I thought was very useful, where she just reviewed all the things, all the basic information that we already know about language models to get us ready for the discussion about natural language generation, so natural language generation is really important now. It was a hot topic even then, but right now, you know, conversational AI and chatbots and so on are very fast, rapidly developing field. Applications that allow you to make an appointment, you know, an appointment over the phone for a hairdresser or for a doctor, or so there's a lot of different applications of this. And then I've even seen, I know Andrew Ng has explored as early as last year. He actually has a company that it has a chatbot that acts as a counselor, as a psychological counselor, and talks to you about cognitive behavioral therapy and so on, asks you questions and so on. So there's a lot of uses of this that you can imagine. I mean, if people could access a counselor online without paying so much and having to drive there in person, and supplying those services via a chatbot would be much cheaper than having a person who's an experienced counselor to talk to. The possibility of having mental health services at very low cost available to very many people is just one possibility for chatbots. So with that, let's go through this recap. So, okay, so natural language generation is a subcomponent of machine translation, which we've seen, translating from one language to another. Abstractive summarization, which we've seen, and we'll talk a little bit about what that is more precisely. Dialogue, chit-chat, and task-based. Chit-chat would just be having a random, having a conversation. You know, you say something, and then the chatbot says something interesting, and then you say something back, and so on. But the task-based dialogue would be more like on the lines of setting up an appointment for a doctor or for a dentist, or again, getting cognitive behavioral therapy, mental health services, and so on. That would be more example of a task-based dialogue. And then, of course, there's the creative writing and storytelling and poetry generation, trying to get the computer to write things that, prose and poetry and stories and so on. And that's been in the news a lot because the GPT-2 and GPT-3 do a pretty amazing job at these kind of tasks. They put together text that's interesting and seems to make some sense and so on, and is very entertaining. And then there's free-form question answering. So you ask a question, and then maybe with respect to some document or set of documents, and then the chatbot would generate an answer, but not just extracted. In other words, the squad and squad 2 tasks that we've looked at, those are what they call extractive summarization, where you give the computer some document, and then or a paragraph of a document, or a few paragraphs of a document, and then you ask a question, and then the computer finds the few sentences in the document that come closest to answering your question. So it basically extracts an excerpt of the document and answers your question. But abstractive text summarization means that it actually puts together an answer to the question on its own. In other words, it takes in all the information and then generates some text that tries to answer the question. And then, of course, the thing we've also seen is image captioning. You give it an image and it tries to come up with a short description of what's going on in the image. To me, that's really amazing that a computer, that a machine learning can do that. Okay, so then here's the recap. Language modeling is the task of predicting the next word given the word so far. So you have, this isn't quite edited right. It's probability of YT conditioned on, there should be a straight bar there, conditioned on Y1 through YT minus 1. So the words that came before, what's the next word? And that's what we all know about, that's what we all know that language modeling does. Okay, and then a language model is a system that produces that. It's basically, you can get this if you have the probability distribution. If you have the joint probability distribution of all the words and so on, you can calculate the conditional probability of the next word being based on all the previous words. And then this is just an abbreviation. If you made a language model based on an RNN, it's called an RNN-LM for language model. Conditioning language modeling, conditional language modeling. This is kind of a nice description. It's the same task except based on the words that went before plus some extra input. And so some examples of that are machine translation. X is the source sentence that you want to translate, and Y is the target sentence. Summarization is also an example. X is input text and Y is the summarized text. So you're building up Y, you're building up a sequence of words Y given an input that do the best job of summarizing it. Dialogue, the same thing, also a conditional language modeling task. You have the history of the dialogue so far, and then Y is the next utterance or sentence. Okay, and this is just a review of a conditional RNN-LM. We've seen this. This is like a machine translation. So you have the encoder RNN, and the hidden state output goes into the decoder RNN. And when you're training the model, you have access to. So this is a French sentence, and this is the you want to translate it to English. And when you're training the model, you have the translation, and so you have the encoder part and the decoder part, and then you get your loss function that you then minimize. Okay.
Sorry, Joseph, you couldn't share your screen because we can't see the slides.
I'm very sorry. I thought I was sharing it. I'm so sorry. I should have checked. I always do this. I always check at the beginning to see if I'm sharing my screen. So sorry. Thank you for speaking up. Okay, let me do this. I think I shared my screen and then I did something by manipulating the windows, and it stopped sharing, and I didn't notice it. So let's see. There it is. Yeah. Can you see it now? Yeah,
that's it now. Yep.
Okay.
Cheers.
Okay, let me back up to see if there's any miss. So this is what I've been going over, the slides that we talked about. Natural language generation, and then all the different examples of natural language generation. the recap, the language modeling, predicting the next word, conditional language modeling. So this is supposed to be this conditional probability. It's missing a bunch of brackets. There should be a straight bar here. So you're predicting the next word, yt, conditioned on the series of words y1 through yt minus 1 that go before it, plus this extra input that you're considering. So there should be a round bracket here, a round bracket here, and a straight bar here. So conditional language modeling is, so back up a second, language modeling is just where you have, you're getting the next word based on, so there's a straight bar here, you're calculating the probability of the next word based on a set of words that went before. That's an ordinary language model. Conditional language model, you're conditioning the next word not only on the words that went before it, but on some other piece of input. And so then they mentioned examples of that as 3 examples of machine translation, summarization, and dialogue, where X is these different things. Okay, so now just a visual of an RNN. We've seen this before, language modeling, a language model that does machine translation. So you have a French sentence that goes into the encoder, and then the hidden state comes out and goes into the decoder. You're training this model, so you already have the English translation, and then you build a model that learns how to make that English translation, minimize that loss function. There's one thing that she mentioned here called teacher forcing, and I think I've seen that, but I'm not really, I didn't really get exactly what it is. Does anybody know what the exact definition of teacher forcing is?
I think it's just to do with the fact that, like, at the bottom of the decoder, they put in the next word each time. So yeah, like when they're training it, it's telling you exactly what the word is as opposed to putting in the word that's actually being predicted. So it's forcing the decoder to learn the next word.
So that's just so teacher forcing is just the way you train the translation, the machine translation model.
I think so, yeah. So like, you know, like last week when we were doing the transformer where it would like mask out the next word,
yeah,
and it would do one word at a time. So as far as I'm aware, that's it. So yeah,
that's it.
because like that.
You're right, Steve. Instead of connecting
when
the
you're
output,
running in,
go ahead.
Yeah, because when you run at test time, you don't have those words, obviously. So at test time, you get the next word by your last prediction, where at training time you do have the words, and then you force it to learn the next word.
Oh, okay, I understand. So that's just the situation that holds when you're trying to train a language model based on, based on a training data set. You have pairs of sentences, one in English, one in French, and its corresponding sentence in English. So that's different than a language model where you're basically training it on itself. You're training the text corpus on itself, predicting the next word. Okay, I get that.
And in fact, when you train the translation model, otherwise without teacher forcing, you just feed the output coming out like J1 back into the next decoder and J2 back into the next decoder. And in the teacher forcing, you don't do that. You just let those outputs come out, but then you feed the correct answers from the bottom.
So you're saying that without the without teacher forcing, you would feed this word into the output of this first word into the next word here.
Yeah.
But that's the model. That's when you're just trying to predict the next word in the same language, right? In English.
No, in the translation also you would do what on the left, which is all the from language stuff, and you put that in, feed that into the right side, but each of the words spit out is fed in as the next word to the next step in the decoder if you don't have teacher forcing. But most of the time these days you do teacher forcing, which means you feed the correct word.
Yeah, that makes sense. I mean, and that's the way I remember that we learned how machine translation is done. I don't think anybody tries to, I mean, because then you're throwing away all the information you have about the whole sentence. You're just saying, well, um, I'm going to put this hidden state in here, and then I get this word he, and then I'm just going to see what comes next instead of making use of the fact that I already know what comes next.
But I think that was the evolution along the path of how people came to implement the various things. So there are models believe that were built without teacher forcing. But
So language, I'm sorry, machine translation models built without teacher
yeah,
forcing?
where J1 is fed in, because that's again a conditional, right? It's just the
Yeah.
conditional based purely on J1 being fed in as the input versus the word he being fed in as the input. So that's my understanding, as Steve explained, of what teacher forcing is. And there was, at least my understanding is that there were models built, probably given teacher forcing helped so much that nobody does that anymore. But at some point they did do that.
Okay. Okay. So once you built your conditional language model, you want to use it to generate text. Um, the decoding algorithm is the part that does that. And in our past, we've studied two different kinds of decoding algorithms. One is the greedy decoding, and one is the beam search. So let's just recap these briefly. The greedy encoding is we just take on each step we take the most probable word. That is, you look at the probability distribution of words that could come next, and you just pick the one that's the most probable, and you choose that, and you feed it in on the next step. So this is that non-teacher forcing model that Srinivas was referring to, where you take each output and feed it in as the next input. And then you keep going until you produce the end token, or until you reach some maximum agreed upon length beforehand. And it points out that due to lack of backtracking, I'm not sure what she means by backtracking here, the output can be poor, i.e. ungrammatical, unnatural, or nonsensical. And I think we've all seen examples like that. And then there's the beam search decoding, which I think is in more common use, where the search algorithm doesn't always choose the highest probability next token, but it tries to track in parallel several of the highest probability choices. So on each step, you keep track of the k, where k is some integer, most probable partial sequences, which we call hypotheses, and k is called the beam size. And in this course, we've seen an example of beam size 2, which already looks pretty complicated. But so yeah, keeping track of the two highest most probable choices, and then at the end, stepping back after you've completed the sentence, then you see which one of the partial sequences was the highest probability. So after you reach some stopping criterion, and that means either the end token is reached or you reach the maximum number of some maximum number of words, then you choose the sequence with the highest probability. And then remember, there was some penalty for length. Longer sequences, or wait, I think shorter sequences were penalized, if I remember right. But I'm not sure about that. Does anybody remember whether the penalty increases for length or increases or decreases with length?
I think I agree with what you said. Shorter, I thought, were penalized.
Yeah. Okay. And so here's just an example, and this is the same example we saw in the class. So you have this start, and then here are the, in each case you find the words with the, let's see, I'm trying to see if I can make sense out of this. So here's two choices. These are the negative log, these are the log probabilities, so they're negative numbers. And I'm not sure why there are numbers, numbers, and then words, words. But anyway, it's tracking through several possible trees. You know, you start with he, and then there could be struck, or there could be was, or there could be got, and then one possibility is hit. And then if you take the two highest, you could have, well, in this case, maybe they're not just choosing, well, it says beam size equals 2. I'm not sure where that's evident here, because it looks like 1, 2, 3, 4 words. But anyway, the point is that after you track possible trees of words, and then you find the one with the highest probability. So you don't.
Sorry, Joseph,
yeah.
but in the it seems like the dark mode is playing games with what you have on the screen, because in the uh, white background screen that I'm staring at, it shows that hit is selected, but there are multiple things with the boxes are around all the words, and then
Okay.
sometimes the number is below and sometimes the number is above. So that's why you're seeing it this strange way in the
Okay. Well, let
dark
me see if I
background.
can. See, this doesn't give me a. That
And
doesn't.
there
That's
are
just the background.
choices, multiple arrows going from left to right as well. So
I bet those conditional probabilities were there too in the original document. Remember where they were missing the bars and the parentheses in my view?
yes, they were there. They were there.
Let's see. I wonder how I can fix this. Preferences.
Yeah, sometimes it changes it in the browser, and I've had difficulty flipping it too.
I'm not seeing
Joseph,
how
I think
to.
it was in accessibility.
In accessibility. Okay,
Yeah.
thank you.
No, the same
Yeah,
window.
in preferences, accessibility. That's right. So where
Yeah,
are we?
yeah, second one. After 3D and multimedia. The second one.
Ah, there we go. Thank you. I didn't see it. Okay.
Page background should be white.
There we
Yeah,
go.
black.
And
The text should be black and
that's right. That's right. I'm gonna make this black, and then make the page background white, and that should do it, right? Okay. Let's see what happens. Ah, there we go. Okay. So does this look different? Is this what you're seeing then, Srinivas?
This is different.
Huh.
Yes.
Yeah. So here's the two tracks. So he and then hit and struck. So you're choosing the two most probable words to follow that. But the other possibility is you choose I, and then and then you choose the two possible words that follow that. And so then at each point you make a tree of the next two possible words. Let's see. Why did it not follow the two possible words for struck? Oh, maybe you only keep two. You only keep two. So you keep two for this branch.
Hit and was, which are the two lowest of the four that you get in that particular column, so to speak, and then you proceed further from those two.
Yeah. So then but at each point you only keep two examples for each branch.
Yes, that's the search size, beam size of 2. So you pick the two lowest.
Yeah. Okay. So then this is how the beam size 2 works, and then at the end, this turns out to have the best. This green, the ones in green turn out to have the lowest probability. And so you can imagine that if you do, k equals 6 or something bigger, it gets complicated pretty fast. But at least k equals 2 shows how you can visualize how it works. So this is the difference between greedy and non-greedy. Greedy, you just always take the best, the lowest probability. Non-greedy, you kind of sit back and wait to make up your mind. You say, okay, let's look at the 2 or 3 or 4 or 5 best choices, and then wait till the end to see what we're going to select. And then that way, you will end up with a better. You'll find the global minimum closer to the global minimum than if you did the greedy search. Okay.
Actually, the other thing, if you recall, I also recall the paper that you had shared, which was also quite interesting, that you select all the words that give you above, if I recall, a target probability, and then pick randomly among them. Do you recall that paper?
Yeah, there was top K, and then there was top K words, and then
It's based on the probability cutoff. So
abilities.
if you
Yeah.
say, like, I want all the words which give me 98% probability for the next word, then you take the top 2% probability words and then you pick randomly from among them. And that gave even better results than the beam search stuff. I forgot the paper name though.
Yeah. And I forgot the name of it. The name of that method too.
Technique, yeah.
Yeah. I think she. Okay. So then she talks a little bit more about beam size. Um, K equals 1. Beam search with K equal 1 is the same as greedy decoding. So, and the problem with that is you get ungrammatical, unnatural, and nonsensical and incorrect answers, and incorrect text. Larger K means you consider more hypotheses. So you increase K, you reduce some of the problems. But as you might expect, it's computationally expensive. But this is sort of the counterintuitive part. Increasing K introduces other problems. She says that increasing K too much can decrease the blue score. And this is primarily because large K beam search tends to produce too short translations, even with the score normalization. And that means you're penalizing the short sentences. And then she says, in open-ended tasks like chit-chat dialogue, large K can make output more generic. So in other words, bland and uninteresting and safe. And so I guess she says, here's an example. Give it a prompt. I mostly eat fresh and raw diet, so eat a fresh and raw diet, so I save on groceries. And then here's the answer. Here's the next utterance or the answer or the response given different beam sizes. And beam size 1 looks decent. Beam size 2 looks decent. Beam size 3, that's a reasonable response. And then beam size 4, I am a nurse, so I am a nurse. That doesn't seem like you got anywhere with that. And then from there on, the responses are just, they're not really responses to the text. They're sort of random probes of, and it doesn't get any better. So what she says, I think this is a good way to summarize it. Low beam size, you're more on topic, but you might have bad English or nonsensical. Higher beam size converges to a safe or correct response, but it's generic and less relevant. So it's just, somebody says something, if you're talking to somebody and they say something weird and you want to make the conversation go on, but you don't want to respond to what they said, then you switch to a neutral topic like, oh, the weather today is nice, or, the football game's on tonight. What do you think about that? You switch to a safe topic, but not relevant. It's just a generic topic. So that's kind of an interesting and maybe counterintuitive effect of increasing the beam size. Now she switches to another topic. A different way of doing decoding, it's called sampling-based decoding. Both of these are more efficient than beam search, but you don't consider multiple hypotheses. So that means that, computationally efficient, I think is what she means. So this is what she calls pure sampling. On each step T, you randomly sample from the probability distribution PT to obtain your next word. It's like greedy decoding, but sample the argmax. So to me, this is like random. I'm not sure why she calls it pure sampling, but to me, I think that is the correct sort of word that they use in the field they call it pure sampling, but it's basically kind of like random sampling. You sample from the probability distribution, and Srinivas, I think this next one is the one you were talking about, where you do top n. No, It's not the same as what you were talking about.
I think it is.
But there's a related one. We saw top N,
Right.
but then the one you're talking about is you sample with a threshold, with a probability threshold. Instead of saying, I want the top N words, you say, I want the top N words no matter what N is, but as long as they have more probability than some threshold. So with top N, you always get, N words, but if you sample instead from the probability, if you instead specify a probability threshold, then sometimes you might get 2 words back, sometimes you might get 10 words back, sometimes you might get 5. It's the probability that you set instead of the number of words. Does that ring a bell?
Yeah, that's exactly the one, Joseph. It showed with the paper that you had discussed, which showed much better results than the beam search.
I see. And did it also show better than top N sampling, the way that's described here?
Well, the way it's described here was what the paper covered, which is specifying a probability cutoff and then picking randomly from any of the words within that set.
But I seem to recall some variant of this where instead of saying I want the top 5 words, you say I want whatever words come out that are more probable than some threshold.
That's exactly what the first bullet on top end sampling says, though. On each step, randomly sample from PT restricted to just the top n most probable words. So the PT says, like the probability cutoff 98, 99, 95, whatever, and then pick from any of the words that cut off, or any of the words that are returned above that cutoff.
Okay. Okay, so then, but I seem to recall a variant of this where instead of specifying that I want to just choose the top, 5 words or the top 2 words, give me however many words past the probability, I specify, instead of N, I specify a P, and then it returns all the words that pass that probability criterion. So that sometimes you'd get 5 words back, the next time you might get 2 words back, the next time you might get 3 words. I seem to recall a variant of this, that they presented 2 different techniques that were similar. One where you specify N for the number of words, and one where you specify a cutoff probability P instead. Because here, PT refers to the probability distribution of for the next word, and it doesn't specify some cutoff. But anyway, I guess she says here that if you think about top N sampling, if you always want N equal 1, that's the same exact thing as the greedy search. And if you allow N to be all the words in your vocabulary, that's this V, then that's what she called pure sampling up above. You consider all the possible words that come back, and then you pick the most, you pick them, well, you randomly sample from them to pick your next word. So you choose, pure sampling is where you say, give me back all the words, and then just give me and then draw a random sample from them, and that's my next word. Anyway, so she says that the way this could work is you decrease N to get more generic or safe output, and you increase N to get more diverse, risky output. So this makes sense. Like if you choose a small n, like n equals 1, then you're choosing only the most probable word. If you say n equals 5, then you say pick randomly from among the top 5 words. So then you're still pretty safe, right? You're getting. But if you increase n and you say, let's say n equals 100, let's say n equals 10 or n equals 20. Now and you just allow that to be randomly sampled. In other words, you take the top 20 words and then you randomly sample it. You can see how that would lead to more risky or diverse output. You're opening up to lower probability choices. Does that make sense?
Right, Joseph, there are two ways you can specify the selection, and one is using the number of words, or the other is specifying a probability and then picking a word from whatever number of words that are returned when you pick a high probability.
Yes, that's the two variants that I'm talking about, right?
Yeah. So
yeah.
and I think the paper that you had brought up in the fast NLP thing, I thought discussed both
Yes.
approaches, and the underlying theme is what you just hit on, which is human speech. It seems occasionally chooses less likely words, and always selecting the highest probability word defeats that, and therefore causes problems.
Yeah, I mean, human speech has what makes it interesting is that you'll sometimes hear things that you don't expect, and if that's sort of what makes the conversation interesting when you hit on something less probable and so on. But if you always choose the safe option, the most probable option, then the dialogue won't look very interesting. I don't remember those, Srinivas. I don't remember which of those two methods, I think they did call it top K in that course. Top K, and then the other one that you refer to is choose a probability threshold instead, and pick from among those. I'm not sure what that was called, and I also don't remember when they compared them which one turned out to be better. But I think it was the top. It wasn't the top K. It was the other one where you choose a probability threshold and consider all the words that pass that threshold, and then you pick randomly from among them.
Yeah, that's my recollection too. But
anyway, yeah. So I guess the most important takeaway from this discussion is that beam search has limitations, and one of them is that there's a sweet spot, and you don't really know what that sweet spot is, so you kind of have to, and you can't really tell at first like what your beam size should be. And then the second thing is to find that out, you would have to do lots of experiments with large beam sizes, and that's computationally not efficient. So I think this method is preferred. This top K sampling method is preferred over beam search. At least that's what I got from this discussion that she gave. And then she reviewed this other thing that we had also looked at called the Softmax temperature. So on a time step t, the language model computes a probability distribution by applying the Softmax function to a vector of scores. And remember how the Softmax function works. It's just the exponential of a score divided by the normalized by the sum of all the possible scores, the exponentials of all the possible scores, and that turns the score into a probability. But she said that you can also apply a temperature hyperparameter tau to the softmax by just introducing it as a divisor, as a normalizing constant when you calculate these probabilities. And she says that if you raise the temperature tau, then the probability distribution becomes more uniform, thus more diverse output. The probability is spread around. But if you lower the temperature, then the distribution becomes more spiky, that is more peaked. So you can imagine that that she's talking about, if you think about a Gaussian, if you raise the temperature, a high temperature means the Gaussian has a broad width, but a lower temperature means that the Gaussian has a narrow peak. And so that means you have less diverse output and the probability is concentrated on the top words. So this is another way of increasing the diversity of your conversation by introducing this tau. And she stresses that this is not a decoding algorithm. It's something that you can use alongside of whatever decoding algorithm you picked. So you can use this with beam search, or you can use it with the sampling-based decoding. Okay, so summarizing, greedy decoding, beam search, sampling methods that we just talked about, the top K. This is good for open-ended creative generation, making poetry or stories. Top N sampling allows you to control diversity, right, by just choosing N to be large or small. And then softmax temperature is another way to control diversity by choosing a high temperature or a low temperature. And remember, temperature is that tau, the funny looking Greek letter for T. It's tau. Okay. Okay. So now she goes into the next section. NLG tasks and neural approaches. Task definition. Single document. Summary of a single document. Multi-document means we write a summary of multiple documents. So here there's one extra input, and here there are n extra inputs, one for each document. The documents can have overlapping content, news, articles about the same event. And then she talks about some data sets for text summarization. I'm not familiar with these, but each one of them has a paper, I guess, that's associated with them. GigaWord, first one or two sentences of a news article. You take the first one or two sentences of a news article, and then you try to make a headline out of it. LCSTS, Chinese microblogging, you take a paragraph and you try to summarize it in a single sentence. New York Times, CNN, Daily Mail, take a news article and give a multi-sentence summary. And then she talks about this new one from last year, I guess, called WikiHow. You take a full how-to article and then you summarize it in a few sentences. So you can imagine that this text summarization is really important for people that have to digest a lot of information and understand it. Instead of reading through some, several thousand-page article, some executive who wants to educate themselves on something like, Bitcoin or something, they can say, okay, here's the articles that people told me I should read. Now, you machine learning model, you look at these articles and summarize them for me. And that way, I get the gist of it without having to actually read it. And that's really, it's like a Cliff Notes thing. So you can see how it's really going to be useful when people get really good at it, when the machine learning models get really good at it. Sentence simplification. Revise the source text in a simple, sometimes shorter way. So simple Wikipedia, take a standard Wikipedia sentence and make it a simpler version. Take a news article and convert it to a version written for children. That's a similar thing. You rewrite it in simple language. That's almost like a translation. It's almost like a translation task. You're translating from English to a simpler version of English. Okay, and then she talks about extractive summarization, executive summarization, extractive summarization, versus abstractive summarization. We mentioned this before. Extractive is where you select parts of a document, typically sentences, and say, "Oh, this is in a gist. This is in a nutshell. This is what it says." It's easier because you don't have to paraphrase. You just pick the sentences that are the most explanatory of what's in that paragraph. The harder task is abstractive summarization, where you have to generate new text that explains the gist of what's in those paragraphs or those documents. And of course, this is more difficult. The Squad and Squad 2 tasks were extractive summarization. They were the easy ones. And now people are, I guess, making progress on abstractive summarization. Then she talks about before neural networks approaches, the summarization techniques. And it's just interesting to go through this procedure that they did. Sentence segmentation, put together all the sentences from documents, extract the sentences that are relevant in some way, order them, simplify them, and then output them into a summary. I guess this must have been a really tedious process. But the point she makes is that pre-neural networks, the summarization systems were mostly extractive. That is just finding the most relevant sentences. Pipeline, we just went through that. Yeah. So Let's see. Okay, so sentence realization and summary. Presence of topic keywords. TF-IDF. So scoring functions based on TF-IDF. And I guess that has to do with TF-IDF, if I recall, is where you renormalize the word probabilities to eliminate the frequent words that don't mean very much, like the, and so on. And then, so let me try to remember what this TF-IDF means. In text frequency dash IDF inverse document frequency, this refers to some kind of a normalizing thing that's the logarithm of the word frequency among in all the documents. I don't remember exactly what this formula is, but it has to do with how new the word is, how surprising the word is. You sort of normalize all of the weights of the words to remove all of the uninteresting words and then give a measure of how frequent or of how rare this word is among all the documents that you have that you're choosing from. She talks about features such as where the sentence appears in the document, like I guess towards the middle, towards the beginning, towards the end. Graph-based algorithms document as a set of sentences. Each sentence is a node and the edges between each sentence pair. And I guess the edges have to do with similarity, so there could be some kind of like a cosine similarity score. And then she says use graph algorithms to identify sentences which are central in the graph. I'm not sure how that will work. It would be nice to have a document, a sort of a diagram here to show what this is referring to. But you can imagine the central sentences are the ones that have the most connections to other sentences. Anyway, now she introduces a score for summarization. You have to have an evaluation score. So she introduces this new metric called ROUGE, which is obviously intended to be related to bleu, because it's the French word for red, and bleu is the French word for blue. So this is called recall-oriented understudy for gisting evaluation. You can see that it's a contrived acronym to make up the word ROUGE. So it's based on n-gram overlap, no brevity penalty, and ROUGE is based on recall, while bleu is based on precision. I didn't realize that actually when we studied bleu. Recall, remember, is the fraction of detections that you make, the fraction of correct detections that you make. That's what recall is. And I think precision is, let's see, I think it's one, okay, I'm just thinking of in a two-class model, recall is the fraction of correct detections that you make, whereas precision is, I think it's 1 minus the fraction of correct negative detections. I think precision is 1 minus specificity, and specificity is the fraction of correct negative detections. So I understand what recall and precision are, but I'm not sure that I understand what they are in the context of these scoring metrics. Let's see. So this is a sum over n grams, where n goes from 1 to 4 or whatever. I think in blue it's 1 to 4. S is a set of reference summaries. So these are maybe candidate summaries. And then you sum over the number of grams, like 1 grams, 2 grams, 3 grams, 4 grams, and so on. You count the number that match. And let's see, I'm not sure what match means in this context. But on the denominator, you sum over all of them. You count all the grams. So the numerator and the denominator are different by this word match here. I don't understand this sentence here. Precision is more important for machine translation, and recall is more important for summarization. But then she says that in practice, people use an F1 combination, a combination of precision and recall. And remember that F1 is the harmonic mean of precision and recall. So she says that in practice, people incorporate both precision and recall in the ROUGE metric. And I think that in order to understand this really, understand this formula, she doesn't really explain it. I think you'd have to go in and look at this paper, which I admit that I haven't done.
Joseph, it's just how many n-grams got matched between the
Ah,
generated summary and the gold label or whatever.
okay, right. That makes sense, Gautam. So you have a training set where you have summaries, where you do have the summaries that some humans have come up with.
Yeah.
And so what Gautam is saying is that, I think, is that you're counting the number of n-grams in your summary that matches the n-grams in the gold standard summaries.
Yep.
Okay, that makes sense. And there's no penalty for brevity. So as long as you are, as long as you're matching, let's see. So what happens in the numerator? You have you have a certain number that match, and you count those. In the denominator, you count all of the grams that you came up, all the n-grams that you came up with. Yeah. So if
Total number of
among
matched n-grams by total number of n-grams.
yeah. So if only a small number of n-grams match, if only a small number of your n-grams match, then you get a low score. And if a large number of your n-grams match, then this sum is closer to 1, you get a better score. Okay, so that makes some sense. But I still don't understand this precision recall thing. Precision. So precision, I'm thinking that precision means, sorry, recall means that you demand that you detected all of these n-grams, that you matched all of the n-grams that were in the gold standard set. Yeah, I mean, that's what's being stressed here. This score actually gives you a high score for high recall. So now I understand that.
Yeah,
The ROUGE
the
score,
key says how many of the relevant items are selected is recall. So that kind of makes sense, meaning
yeah,
how
that's what
many
you're
are
doing here.
therefore the match, right? How many
Yep.
relevant
Yep.
things were selected is recall, and precision is more how many of the selected items are relevant, which would matter in translation. Because you want to select those that are relevant. Here, how many of the relevant ones are selected?
So, yeah. So, okay. So I guess it's really good what Srinivas is doing. Going back to the Wikipedia because they give a very excellent article on the definitions of all these terms. So relevant. How many of the relevant items are selected? That means like what fraction of detections, what fraction of true detections did you make? In other words, of all the examples. Of all of the true examples, how many of them, what fraction of them did you detect? That's what's called recall. And then the other way is among all of your, all the things that you labeled positive, how many of them really were positive? I think that's what precision is. So in other words, that, let's see. Yeah, so that would be like and the denominator would be all of the positive things that you labeled, including all the false alarms that you labeled positive, false detections. And then the numerator would be the number of actual positive detections that you made among all of the ones that you said were positive. Does that make sense? Maybe I'm going to go to that page that you because I remember that page. I'll just share that page. Let's see.
Actually, I failed to see the difference between precision and recall in this text generation paradigm. Like they both should mean the same thing, right? How are they different exactly? You
Well,
would
let's
still
look.
have to find out the match of n-grams divided by. They seem like the same for both precision and recall.
Okay, so here's the definition of precision and recall. Recall is like how many relevant items are selected. So the true positives in the numerator among all of the
Okay, yeah, the denominator would be different. In recall, the denominator is how is the n-grams in your gold label, whereas for precision, the denominator would be n-grams in the generated summary. Yeah, I think I got it now. So recall is basically how many of your n-grams from the gold label are you gold human text are you able to recall. So your denominator would be n-grams from the gold text, whereas for precision, out of all the n-grams the model generated, how many are actually there in your gold text. So the denominator would be the n-grams in the model generated text.
So let's see. I'm not quite following you, but I think it makes sense what you're saying. Can you explain that again? So we're looking at recall.
So recall is how many n-grams from the gold text were you able to recall?
What fraction of them? What
Yeah.
fraction of them?
So
Yeah.
the numerator is the matches of n-grams, and
Yes.
the denominator is all the count of n-grams in the human gold text, human
Yes.
written
Yes.
text. Whereas for
Okay.
precision, the numerator is the same. The denominator would be all n-grams in the model generated text, because you're seeing how many of the n-grams
Yes.
generated by model match with the gold text.
Yes. So in this case, the denominator includes all of the false matches, all the false positive. It includes all of the n-grams that you generated, whether or not they were the right
No,
ones.
in ROUGE, it would be all count of n-grams in the human written summary.
Yes.
Because you
That's
want to
this
see
one.
what fraction of that you were able to recall.
So, so you're saying that ROUGE is actually stressing precision.
No, ROUGE is recall. So recall is basically how many of the uh, n-grams in the human written summary were you able to recall. So the
Yes.
denominator would be n-grams, number of n-grams in the human written summary, right?
Yes. 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 And the numerator is the matches.
Yeah.
Right. So, as we said, then the ROUGE is actually emphasizing recall. I'm not sure why she says that bleu is based on precision. Bleu is, if I remember what it is, it sums over the 1 grams, 2 grams, 3 grams, and 4 grams, and asks how many of them you got, how many of them you actually hit on.
So blue would have the same formula except the denominator is different. So how many of your predicted n-grams actually match with something in the human translated text?
Okay, okay. Thank you for that. So yeah, so that gives a little more insight into how ROUGE is based on recall while bleu is based on precision. That wasn't clear to me as I was going through that. I want to make sure that I'm still sharing the original PowerPoint from the Stanford lecture. Is that what you're seeing?
Yes.
Okay, thank you. Okay, so let's go on. Bleu is reported as a single number, the combination of the precisions for all grams up to 4. ROUGE scores are reported separately for each n-gram. Okay, so that's another difference. So if again you specify 1, 2, 3, and 4 grams, then you'll get 4 ROUGE scores. Most commonly reported ROUGE scores are ROUGE 1, just unigram, ROUGE 2, bigram, ROUGE L, longest common subsequence overlap. I'm not sure what that means. And she says this is a big deal. There's now a convenient Python implementation of ROUGE. I think that was a problem for workers in the field before because the previous one was based on Perl, which is a kind of like, it was big in the 90s, but not a lot of people are using Perl anymore. So, but in order to use it, you had to somehow make a wrapper or something and use it in your, because nobody was coding NLP in Perl now. So anyway. So now she's summarizing the state of neural summarization. Neural summarization means text summarization based on neural networks, 2015 to present, and in her case, present is 2019. Okay, 2015, the first seek-to-seek summarization paper, single document abstractive summarization, and she says that it's a translation task, and that's an interesting view. Standard seek-to-seek plus attention NMT methods. Let's see. So here's the document you're trying to summarize, or the longer sentence, and then here is a shorter sentence. And I guess they're showing the attention model, where dark is more attention. So here are all the words in the original document, and where's the attention concentrated? Called Joint Front Combating Terrorism. So those are the words that it identified the attention on, and then it put those words together basically and came up with this phrase: Russia calls for a joint front against terrorism. That makes sense. Since 2015, there have been lots more developments. I'm sure that in the time between 2015 and 2019, I'm sure that in the time in the year that has passed, or the year and a half that has passed between when this course was given and now, there's probably as many new developments as there were between 2015 and 2019, because the field is really accelerating. Hierarchical attention, multi-level attention, more global, high-level content selection. I'm not sure what that means. This is something new. Use reinforcement learning to directly maximize ROUGE or other discrete goals. I don't know anything about reinforcement learning, but I think from what I've seen in context is that when you're trying to minimize some function that is not convex, stochastic gradient descent can't handle those kind of problems very well, but apparently reinforcement learning can. It can minimize non-convex objective functions, and I think that's the feature of reinforcement learning that is being used here. Graph algorithms. Okay, so these are ideas, but I'm not really sure. Again, you'd have to read this paper to understand what she's doing. Uh-oh. Oh, I thought I went back to the dark text. Copy mechanisms. Seek-to-seek and attention systems are good at writing fluent output, but bad at copying over details, like rare words, correctly. Copy mechanisms use attention to enable a seek-to-seek system to easily copy words and phrases from the input to the output. That sounds similar to like an identity connection or something, like when we were talking about CNNs, where the identity connection would guarantee that you don't lose some of your input. And it sounds like that's what the copy mechanism, it's similar to that, so that if you had a rare word in your input, you would keep that in your output. Allowing both copying and generating gives a hybrid extractive-abstractive approach. I guess that makes sense. Okay, and then there's papers. Again, I haven't read any of them, but these talk about different copying mechanisms. And then here's a detail of one of these models. I'm not going to actually go over this, but let's just keep going. Big problem with copying mechanisms, they copy too much, long phrases and sometimes whole sentences. So you can imagine that would be a problem if you're so concerned with not losing your input that you're preserving too much of it. What should be an abstractive system collapses to a mostly extractive system. So I guess you have to, it's all about finding the sweet spot and giving the right weight to the copying mechanism. Another problem, they're bad at overall content selection, especially if the input document is long. There's no overall strategy for selecting content. Okay, that makes sense. Better content selection. I guess this is where the, okay, standard seek-to-seek attention summarization systems, two stages are mixed together. That is the content selection and the surface realization. So this is a technical term, I guess, and this refers to just the generation of new text. And content selection refers to keeping interesting words that come in your input. So you can imagine that there's some kind of a sweet spot where you adjust the weights of these so that it's generating enough new text to make it interesting, but it's also keeping enough of the important words, it's not throwing them away. So mix together these stages in standard seek-to-seek attention summarization. These two stages are mixed together. On each step of the decoder, that's the text generation, we do word level content selection, which is by attention. And she says this is bad, no global content selection strategy. You're just doing it sort of on the text in front of you. Then she talks about a solution, bottom-up summarization. Content selection stage, use a neural sequence tagging model to tag words with tags such as include or don't include, keep or don't keep or throw away. And then the bottom-up attention stage, the system can't attend to words tagged don't include. So it's basically applying a mask. So instead of just throwing the words into the seek-to-seek attention model, you do some kind of pre-processing by tagging each word with a tag, keep or throw away, include or don't include. And then when you pass it to the seek-to-seek attention model, you say, well, mask off the words that are marked don't include. And I guess that has been shown to be effective. Less copying of long sequences, so that you don't get, so that means less extractive output and more abstractive output, better overall content selection strategy. So here's the schematic. You have the source text, you mask off the words that your sequence tagging model says to don't include, and then you throw it into the seek-to-seek attention model, and then that seems to give better results. Again, there's a paper. I didn't read it, but that's where this comes from, I guess. And then here's where the reinforcement learning comes in. Use reinforcement learning to directly optimize ROUGE-L. Again, I don't know what ROUGE-L is. I wasn't quite sure what it was from her description. I guess you'd have to read the paper to really understand it. Standard maximum likelihood training can't directly optimize ROUGE-L because it's a non-differentiable function. Okay. Using RL instead of ML got higher ROUGE scores, but lower human judgment scores. So that means that when humans rate them, even though it's kind of like they're gaming the system. They got higher ROUGE scores, but then when humans rate them, they rate them they say this isn't that human-like. So apparently it's a double-edged sword. You're gaming the system, but it's coming out with a lower human readability score. Barely readable summaries, but high ROUGE scores. So that must mean that something's wrong with the ROUGE metric. So ML alone, machine learning alone, gets readability, gets these readability and relevance scores. Reinforcement learning alone gets lower readability, but still good relevance. Machine learning and a hybrid approach of machine learning and reinforcement learning gets the best of both worlds. So that's what that's telling us. Now she's moving to the dialogue task, where you're trying to have a two-way conversation where you're making an interesting conversation. But it could be it could be just to make chit-chat for fun, or as I mentioned before, for therapy. Well, no, I didn't mention this before, but just, I guess, somebody who's isolated, especially in this time, there's a lot of people who are isolated. They can't go out. They're in their own houses. They don't have other people living with them. For them, talking with a machine might pass the time. You know, talking with a dialogue, chit-chat might pass the time and help them to feel good because they're doing something they're interchanging their attention with some entity that isn't a human being, but at least it makes interesting conversation. And then there's the task-oriented dialogue where you're assistive, which is customer service, giving recommendations, question answering, helping somebody to buy something or book something, and then cooperative, two agents solving a task together through dialogue. And then there's adversarial, two agents compete in a task through dialogue. So I understand this assistive. I'm struggling to come up with examples of two agents solve a task together through dialogue. I suppose that could still be making an appointment, even a simple appointment for for a doctor's appointment. You still have two agents. The doctor says, okay, here's the times that I have available, and then the other agent is you, and you say, well, here's the times that I have available, and then together you solve the problem by finding a time that both of you are available. So I think that's a simple example of a cooperative. Adversarial, two agents compete in a task through dialogue. I'm not sure what that would be. Maybe you could have two people trying to find out who can tell the funniest joke or something like that. Does anybody have in mind any examples of cooperative or adversarial task-oriented dialogue? No? Okay. So open-ended free-form dialogue systems are a thing now. People are trying to, and we see that the papers that introduce GPT-3 are always, and even GPT-2 before it, were stressing what a surprising level of conversation, of storytelling these systems have. So this, of course, this was before, I think this class was before GPT-2 even came out. So things have gotten even better since then. Here's the papers that she refers to. Again, I didn't read them. Overview of neural conversational AI work. But now she's identifying, okay, so everybody's up until that point is using, or they're still using, I guess, seek-to-seek plus attention methods. Serious pervasive deficiencies for open-ended chit-chat dialogue. Genericness, boring responses. Irrelevant responses not sufficiently related to the context. Repetition, we've seen that. Lack of context, not remembering the conversational history. Lack of a consistent persona. And then she goes into some of the problems and their solutions. So irrelevant response problem, generate response that's unrelated to the utterance, either because it's generic, or it's changing the subject to something unrelated. And one solution that she mentions is, and there's a paper that discusses it, is optimize for maximum mutual information between the input and the output, which makes sense, I guess. And here's what it would look like. The log of the joint probability of the input and the output divided by the product of the probabilities of the input and the output. And so you choose for response, you choose the, of all your responses, you choose, of all the responses you're considering, you choose the one that maximizes the mutual information. And let's see, this expression here is related to this one because the definition of conditional probability is joint prob. So if you're looking for, so it turns out that P of S and T is equal to P of T conditioned on S times P of S. I wish I could write this. I guess I can write it if I do if I get my pen. Let's see. So the point is that this, it makes sense. These two expressions are equivalent, and I want to just show that. Annotate. I'll get my crude pen and try to draw something. So it turns out that the definition of conditional probability is based on this equation. P of S and T, that's what this comma means. The joint probability of the events S and T both occurring, that's a comma, equals P of T conditioned on S times P of S. So I forgot, this is one of the elementary rules of probability. I can't remember what it's called, but it's a basic statement in probability theory. And so by dividing both sides by P of S, you come up with this equation. P of S and T divided by P of S is the conditional probability of T conditioned on S. So now, if you take this, then it's this, right? And so the log of a quotient is the log of the numerator minus the log of the denominator, and that's exactly what you have here. This piece here is the numerator, P of S and T divided by P of S, which is the same as the conditional probability. And the denominator is P of T, so the log of the quotient is the difference, the log of the numerator minus the log of the denominator. Does everybody see how these two are the same? So maximizing mutual information is a way to get around the irrelevant response problem, and I think that's kind of interesting. Okay, I'm going to stop. I'm going to erase what I wrote. Let's see, how do I do that? Yeah, clear all drawings. There we go. Get me back my pointer. There. Okay, so there's that, how to deal with the irrelevant response problem. Then there's the genericness or boring response problem. And she says that the easy test time fixes are directly upweighting the rare words during the beam search. So upweighting the rare words means that you're going to say something more surprising or interesting. Use sampling decoding algorithm, which we went over, rather than the beam search. That also helps to solve the genericness and boring response problem. Conditioning fixes. Condition the decoder on some additional content, i.e. sample some content words and attend to them. Not sure how that gets done in practice, but again, she gives a paper here that discusses it. Why are sequence-to-sequence models so dull? That's a good title. Train a retrieve and refine model rather than a generate from scratch model. i.e., sample an utterance from your corpus of human written utterances and edit it to fit the current scenario. So you're kind of biasing the model to produce more human-like or interesting utterances. Although it's not clear how this is done in practice, but I guess the paper makes it clear. Repetition problem. Simple solution is directly block the repeating n-grams during a beam search, and she says that's usually pretty effective. More complex solutions, train a coverage mechanism and seek to seek. This is an objective that prevents the attention mechanism from attending to the same words multiple times. That makes sense, too. Define a training objective to discourage repetition. If this is a non-differentiable function of the generated output, then I guess I made a mistake before. When I was talking about why reinforcement learning is good, I said that reinforcement learning works on non-convex optimization problems. I think that gradient descent can also work on non-convex problems, but I think the main distinction is that reinforcement learning works on non-differentiable problems. So you have an objective function and you don't have any idea how to compute its derivative. Then you can't use gradient descent because you don't have any gradient. And then that's when reinforcement learning works. So if the training objective is non-differentiable, then you can use reinforcement learning to train it. Again, I don't know much about reinforcement learning, but apparently it works on non-differentiable objective functions. She actually skipped this one and this one. A whole bunch she skipped down to 4, and she took it back up here. So conversational question answering, there's a new data set from Stanford, that's last year, CoQA. It sounds like those vitamins that they sell at the drugstore, CoQ or something like that. Okay, answer the question about a piece of text within the context of a conversation. So here's a conversation, but you have to, the answer has to be abstracted. You can't just copy a piece there. So it's both a question answering and a reading comprehension task and a dialogue task. So here is a paragraph, and then let's see, what's R? Oh, okay, so you not only have to give an answer, which looks like it's a one-word answer, or maybe several-word answer in this case, but you have to give a rationale as to why you chose that answer, or that something that supports the answer. Just going to sit in a rocking chair. Today was her birthday, and she was turning 80. Now that looks extractive to me. That doesn't look abstractive. How old would she be? 80. She was turning 80. That's again extractive. Does she plan to have any visitors coming over? Yes, her granddaughter Annie was coming over. That's again abstractive. Every case I see there's the answer is, oh, okay, it's the answer that gets abstractive, that is abstractive, not copied, but the rationale is extractive. In other words, it just identifies a sentence that supports it. So question 4, how many visitors? 3. Wow, so this is impressive. Like, how many visitors? It counts the number of visitors. I guess it gets it wrong. Let's see. Oh, granddaughter. No, it gets it right. Granddaughter, daughter, and husband. Yeah, so the rationale is extractive. It just says these are the portions of the text that I used to figure out the answer. But the answer itself is abstractive. Okay, you're answering. This is kind of an impressive skill. So it actually figured out that there were 3 visitors coming, and it gave the justification for that. Okay, so that's conversational question answering. Storytelling, usually using a prompt. That's the ones that we see all these impressive results from GPT-2 and GPT-3, where they give you a prompt and then they come up with some really interesting story that followed on that they wrote. So given the prompt, you generate the next sentence or paragraph or whatever. And let's see, different than the previous two because we're not concerned with the system's performance. The previous two being conversational question answering and negotiation dialogue, which we didn't go over. Neural storytelling is taken off. The first storytelling workshop in 2018. It held a competition, generate a story to accompany a sequence of 5 images. That's interesting. So the prompt doesn't even have to be words. It can be images. And I guess this is the paper that describes that workshop and its main results. Generate a story from an image. So you start with an image, and then I'm not sure how this works. Is that are you limited to Taylor Swift lyrics to choose something that goes with the images, or I'm not sure how this worked. What's interesting, this isn't straightforward supervised image captioning. There was no paired data to learn from. So this would be the paper or the blog to read about it. I'm not actually sure what's going on here.
I think
It
it's
starts
like
with
style transfer, like in the style of Taylor Swift lyrics. Like you do style transfer in images, the
yes.
style of paintings of certain painters. So
Yeah,
similar
like
to that.
Van Gogh. Yeah, I see.
Yeah.
That makes sense. So you have to answer in the style of Taylor Swift. So these aren't real Taylor Swift lyrics. They're just lyrics written in the style of Taylor Swift. But how did they get them given only an image? That's what's weird. I mean, even from this image, well, I suppose you could get night sky out of it because you have a lot of dark pixels in it. Dark, again, a lot of dark pixels, but there's also a lot of bright pixels too. In fact, maybe slightly less. My eye sees slightly less bright pixels than dark pixels, but almost equal numbers. So it's hard to see how it came up with this, which has night and dark in it, and nothing referring to the bright portion of the image.
I think it got the light bulb in the night sky part from
Oh,
the
light
experience.
bulb. There we go.
Yeah,
Light bulb. Yeah,
that's
okay.
what it got from the image probably.
My guess is that it says model Taylor Swift lyrics, so you probably get a bunch of Taylor Swift lyrics which are text, and then you get an one or sequence of images, and then you're supposed to generate a story.
Yes. Yeah, you're only allowed to use Taylor Swift lyrics to choose from, to choose your, I guess that's your input, is the Taylor Swift lyrics. But what I don't understand is how it knows anything about the image. I mean, all this is a set of pixels, and how does it know anything about the images?
Yeah, I mean, my again guess without reading the blog or the post is that you have caption generation of images anyways as a text task that's done. So you would probably go through that process and then use some mapping of those words into something from the Taylor Swift lyrics.
That makes sense because, as you say, image captioning, there are supervised database. It is a supervised problem. They have you can get a trained model that does image captioning. Starting with, I don't know, ImageNet images. So you start with that model, you generate a caption. So you start with that trained model, you generate a caption, and then you try to translate it into Taylor Swift ease. I think that would be, yeah, I think that's what you said, right?
Yep, something like that.
Yeah.
So that you have some, from the image or images, you go to words, whatever those words happen to be, unrestricted by model lyrics, and then you do a conditioning on the model lyrics and spit something out.
Yeah. So what was puzzling me at first is where would they even start from? But as you pointed out, they have trained models that do image captioning, and that would be the starting point. Yeah. All right. How to get around the lack of generating a story from an image. How to get around the lack of parallel data. I'm not sure what that means. Use a common sentence encoding.
The parallel data is the problem you're talking about, that it's not a supervised, hey, this image, this set of words, and then, so there isn't that parallelization, if you will, from images to words in Taylor Swift lyrics.
So here's what you were saying. You actually use this COCO data set, which is an image captioning data set. So I guess you use a model trained on COCO. Now, she introduces this thing called skip thought vectors, a type
and
of
for those
general
of
purpose.
us, maybe Gautam has already seen this, but just a plug. Interestingly, the Kaggle competition that we are looking at, apparently that one of the ways early on, and now everything has moved to transformers and stuff, but one of the methods that's talked about in the Kaggle competition question comparison of the Cora dataset is the use of skip thought vectors, which is used to apparently paraphrase sentences. Now, what Gautam has used of whatever, I think, is that universal sentence encoding, Gautam? Is that the...
Yep.
Yeah,
USC.
so that test probably superseded this, but if you go back and look at one of the ways that the sentences were translated into summarized embeddings before the universal sentence embedding was the use of quote unquote whatever the skip thought vectors mean.
Okay, well, this is new to me, but since you guys have been thinking about this, maybe Gautam, can you maybe summarize this page, if you?
I don't think I could do a good job. So
Okay.
USC is just a sentence embedding. I have not heard about skip thought vectors
Okay.
actually.
Okay. So it's some kind of sentence embedding, right? Sentence encoding
Yes,
space.
it's essentially a sentence encoder. So a skip thought vector is something that tries, and again we can look at it in the Kaggle competition context later today. But the skip thought vector is my simplistic understanding without reading the paper. Just what is the evolution? It's a generation of embedding which tries to capture the semantic of a sentence.
Okay. So you find sentences that are similar to it, sentences that have similar embeddings, or?
So yeah, exactly. So you generate embeddings of sentences which capture their semantics, I think is the skip thought. And that means that if two skip thought vectors are similar by whatever metric, then they would have similar meanings. That's, I think, the intent.
Okay, so you start with the sentence, a quote unquote sentence that comes from the COCO caption, the caption returned by the COCO model. And then you look for sentences in the Taylor Swift data set that are similar to
Exactly.
it.
Yes.
Okay.
Yes.
Okay. Well, that makes sense. Okay.
So you've
Thank
come
you.
up with some meaning using using the image captioning. So that image caption has generated an embedding which has some meaning, embedding of a sentence which has some meaning, and then you look for a similar sentence or sentences in the Taylor Swift or the model reference.
Okay, so that makes a lot of sense. So, but now you're saying, Srinivas, that even that interesting method has been superseded by something more
Yeah, I mean,
powerful.
the universal sentence encoder didn't exist, I don't believe, when the skip thought vectors were done. And the universal sentence encoding that Gautam used and showed last week in the Kaggle thing is, I believe, enhancement or progress further along the lines of generating sentence encoding, which is what the skip thought vectors did.
Okay. Okay, great. Now we've got 5 minutes left. I want us to end at 9:45 so that people can just take a break and get ready for the Kaggle meeting. But we have like 35 more slides to cover. Actually, she skipped a number of these. Let's see. Let me just go through these. I took notes so I know where she skipped. Let me see. Let's see. There it is. Okay, let's see. So bottom up, relevant response, position, slide 48, storytelling, Coco. Okay, so then she covered this slide, and the next one. So generating a story from a writing prompt, complex seek-to-seek prompt-to-story model, convolutional based, makes it training faster than an RNN-based seek-to-seek. Gated multi-head, multi-scale self-attention, blah, 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 model fusion. Pre-train one seek-to-seek model, then train a second seek-to-seek model that has access to the hidden states of the first. The first seek-to-seek model learns a general language model, and the second learns to condition on the prompt. Okay, and then there's a paper discusses that. I don't really have anything more to say there. Generating a story from a writing prompt. Results are impressive, related to prompt, diverse, non-generic, stylistically dramatic. So here's an example of one. Aliens start abducting humans. The last of my kind. What's the prompt, though? Maybe the first sentence is the prompt. Now this looks like a yeah, it looks like something from the Outer Limits, and it sounds like something from the Outer Limits. Very realistic. So, oh, there's the prompt. Aliens start abducting humans. There it is. And then, wow, that's really pretty cool. Here's the paper that it comes from. Then the drawback, she says, mostly atmospheric, descriptive, scene setting, less events and plot. So, it's describing what it hears and what it sees and what it feels and what it, yeah, it's all about the 5 senses, isn't it? The only one left out is taste. When generating for longer, mostly stays on the same idea without moving forward to new ideas. So it's not developing a plot, but it sure is convincing to set the scene there. Okay, now she skips over all of this stuff all the way up to slide 67 to NLG evaluation, neural language generation evaluation. So I guess this is a big deal. You have to have automatic evaluation metrics. So we've already gone over word overlap based metrics, Bleu and ROUGE. I've never heard of Meteor. She did talk about F1 being used with ROUGE so that you're taking into account both the recall and the precision. We know that they're not ideal for machine translation. I guess that's Bleu. They're even worse for summarization, which is more open-ended. ROUGE rewards extractive summarization systems more than abstractive systems. That's what she said. She said earlier that it was possible to sort of game the system, get higher ROUGE scores, but be less human-like. So ROUGE isn't really succeeding at that task of summarization. Worse for dialogue, which is more open-ended than summarization, and similarly for story generation. So dialogue, I guess, is you have a human or no, an agent that says something, and then you have to say something back, and then that agent says something back to you, and it's a back and forth. But then the one they're talking about here is story generation, where you give it a prompt and then it writes a whole bunch of sentences that develop on that. And I think that when GPT-2 came out, which was after this class, we saw some really impressive examples of story generation that weren't limited to these environmental, 5 senses kind of things. It actually did have things happening in them. And we've seen from GPT-3 some even more impressive results. So yeah, the things have moved forward in this field. Word overlap metrics not good for dialogue, and here it shows how human scores are from 2 different groups track each other, but blue scores don't track human scores. Perplexity. So what about using perplexity as a score? Captures how powerful your language model is, but doesn't tell you anything about the generation. So if your decoding algorithm is bad, then your perplexity can still be good. I'm forgetting what perplexity is. It has to do with how much choice you have. Like low perplexity means if you give an answer and it has low perplexity, that means that there's it has something to do with how much choice you have in making that answer. If there's a lot of uncertainty associated with your answer, then the perplexity is high. Can somebody give a more precise? I don't remember the precise definition of perplexity. Does anyone remember? Okay. Word overlap metrics not good for dialogue. Automatic evaluation methods. So she says there's no overall metric, but she says that sometimes it does help. They've made progress by defining more focused automatic metrics to capture particular aspects of generated text. So fluency, probability of what you said with respect to what a well-trained language model says, correct style, probability with respect to a language model trained on the target corpus, diversity, rare word usage, uniqueness of n-grams, relevance to input, semantic similarity measures. So you can devise all of these small specific metrics and put together a battery of them, and then that could help give a meaningful score. Human judgments are regarded as the gold standard, but human evaluation is slow and expensive. But then she points out that even human judges have problems. Suppose that you have access to human evaluation and you don't have to worry about compute time. Does human evaluation solve all your problems? No. Conducting human evaluation effectively is difficult because humans are inconsistent, can be illogical, they lose concentration, they misinterpret your question, and they can't always explain why they came to some conclusion. So that's an interesting point, is that even though we have to rely on human judgments as the gold standard, they're not perfect themselves. I think that's where I'm going to stop here. She talks about human chatbots, new avenues, and then she has her own thoughts on NLG research. Some exciting current trends in NLG, alternatives to strict left to right generation, parallel generation, iterative refinement, I'm not sure what that is, top-down generation for longer pieces of text, alternative, sentence level objectives, incorporating discrete latent variables into NLG, not sure what that means. And then she comes up with some of her own takeaways. 8 things I've learned from working in NLG. The more open-ended the task, the harder everything becomes. Constraints are sometimes welcome. So if you can impose a reasonable constraint on your problem, that can help. Aiming for specific improvement can be more manageable than aiming to improve overall generation quality. That's what we just went over. Using a language model for NLG, improving the language model will most likely improve the generation quality, but it's not the only way to improve generation quality. She says, look at your output a lot. So if you're generating conversations, look at them, and then you can try to understand something where it's going wrong or where it's going right. You need an automatic metric, even if it's imperfect. You probably need several automatic metrics. So that goes back to that set of metrics we were talking about, where you define a whole bunch of small metrics for small tasks and then put them all together. If you do human evaluation, make the questions as focused as possible, so that gives the humans less leeway for making errors. Reproducibility is a huge problem, so please publicly release all of your generated output along with your paper, so other people can look at it. Working in NLG can be very frustrating, but also very funny. And then she gives a funny example with her conversations with her chatbot. Gives an example of weird things that chatbots say. That's it, really. And with that, we'll just